Hi class, today's lesson is about applying Kirchhoff's law. We have already studied Kirchhoff's law and we already know what is Kirchhoff's law, and today we're going to learn how to apply Kirchhoff's law in few examples. This is the most important note from our previous video on understanding potential rise and potential drop for EMF. This too you must also understand class in order to apply in our examples that we are going to talk about later. This is about understanding potential rise and potential drop for resistor. Hi class, we have already learned and state Kirchhoff's law. Now we're going to do is we're going to apply Kirchhoff's law. Alright. So in front of you here you can see a circuit which is referring to figure 15.8 from your Oxford FAJAR reference book in page 105. Okay, in every circuit when we want to apply for Kirchhoff's law, we need to have three arrows. Okay, I'm going to just write here. We need to have how many arrows? We need to have three arrows. Okay, three arrows. We're going to draw three arrows. The first arrow we're going to draw is a current arrow. Okay, next arrow we're going to draw is the voltage arrow. And the third arrow we're going to draw is called as loop arrow. So there's need of three arrows in order to apply Kirchhoff's law. Now if you notice that Kirchhoff's law, some of the examples they don't draw all these arrows, yeah, but they actually apply this concept. So what I'm going to do is I'm going to teach you step by step of how to solve Kirchhoff's law. If you follow this step-by-step process, anything about Kirchhoff's law is thrown to you, the question, you can answer. Okay, because it is all based on concept. Alright. Now some questions, they give you the current arrow and they give you the loop arrow. Then they ask you to find and solve by using Kirchhoff's law. Some questions don't even give you all these three arrows. So you have to start drawing all these three arrows. Okay. So let's do a few examples and we are going to start with example 15.8. Okay. If you see figure 15.8 class, we have here a EMF. Okay. We have a what? A EMF E1. And inside the cell there's an internal resistance R1. I purposely draw the internal resistance like this, assuming that this whole thing is in the cell. It's part of a cell. And same goes to this. This whole thing is part of a cell. So that when you see, you can understand the concept. Okay? You can picture it. So that was the reason of drawing it like this. Okay? Here we have a resistor, external resistor R1. And here we have external resistor R2. If you see in figure 15.8, they have already drawn for you the current arrow. They have already drawn for you what? The current arrow. So we're going to follow what the book has given or what the example has given so that our answers can be the same. So the current arrow which was being drawn by the book will be, you can choose whichever EMF you want to choose here. We have E1 and V2, but we are going to choose E1. We're going to follow the book. We choose E1. So the current that flows from E1, we label it as I, exactly like the book. Okay, and then the current flows here is I, and then the current flows in is I1, and then the current flows here is I2. So this all is current arrow. Okay, then we have here I2. Okay, then here also I2, then I2, and then here I2, here is I1, here is I, and goes back to I. Okay, so when we already have drawn the first thing, we have drawn the current arrow, we can apply Kirchhoff's law. Kirchhoff's law says current that entering into a point, the sum of current that entering into a point is what? Is 0. Okay, so I'm going to take this particular point here, point P. You can either take P or Q. Okay, now if you want to choose the other, this one, it will not help you much to solve the question. So you must take the one that have all the currents, okay, variable. So the first thing, when I apply the current, Kirchhoff's law of current, I know I is equals to I1 plus I2. This one is number 1. This one comes from Kirchhoff current or first law. Okay, where the sum of current entering in equals to the sum of current entering out. So entering in is I equals to the sum of current entering out. Okay, then the next step, after drawing current arrow, I draw voltage arrow. Okay, so I'm going to just I'm going to put this a bit special here so that this is the basic of how to solve the Kirchhoff's law. So I'm going to just draw a box here. Okay, and take some time here. Voltage arrow, current arrow. Okay, now I have to draw is voltage arrow. Okay, go back, flashback that we have studied before this under voltage arrow. The flashback was, okay, for voltage arrow, what was the flashback? The flashback was for a resistor, if the current is in this direction, then the voltage arrow will be the opposite direction of the current for potential rise. Correct? So we draw a voltage arrow where the voltage actually represent potential rise. And if it's a EMF, okay, this will be the direction of the voltage arrow, which is a potential rise. Okay, when I draw the voltage arrow, who I have to refer to? I have to refer voltage arrow to current arrow. I must look at the current. Okay, so now I draw. Okay, first thing, this one and this one, the potential rise will be in this direction. Okay, this one is coming, current is flowing here, so the direction of potential rise will be in this direction. Okay, current is flowing here, so the direction of potential rise will be in this direction. Okay, you must draw the voltage arrow for all EMF and for all resistance in the circuit. Yeah, so for E2 is here, the direction of potential rise will be in this direction. And then this one, the current is flowing here, for the direction of potential rise will be in this direction. And same goes here in this direction. Okay, opposite to the direction of current. Opposite to the direction of what? Of current. Okay? Alright. Alright. So, sorry, this one will be this side. Opposite, yeah? Opposite. Okay, that's a mistake there. This one will be what? This one will be opposite. Correct or not? Because the current is flowing this side, this one will be, the direction will be opposite. Okay, now we have already drawn the arrows. Okay, let me check. Okay, this one is correct, 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 this one is correct. Okay, now after we have drawn the voltage arrow, Then we draw the next arrow, which will be, we call it as a loop arrow. Okay, let me take another color pen. It's called what? Loop arrow, which I'm going to do here. Loop arrow. Okay, now here we can have loop arrow, mean it must be in a closed loop. Closed loop. So in this diagram there are 3 closed loops. Okay, so I'm going to label each point in this diagram. Okay, I'm going to label here A, okay, A, here B, here C, here D. This one already given by the book, P and Q. Okay, so it must be a closed loop. So there are 3 closed loop actually in this. Okay, one is A, B, Q, P, A. 1. 2, P, Q, C, D, P. 2. 3, A, B, C, D, A. 3. Okay, so there are 3 loops. You can choose whichever loop you want, but the one that you choose have to have less variable and easy for solution, mathematical solution. Okay, so I'm going to choose the loop because in this question they are already given the loop. Okay, the book has already given the loop, so I'm going to follow the book. Okay, so the book has given the loop is this side, which is anti-clockwise, which is this side, correct? So I'm going to draw the loop, which is this side. Okay, all right, and then the second loop is also this side, which is okay. So I'm going to use the first thing. I'm going to use the first loop, which is this loop is anti-clockwise, correct? So I'm going to use the first loop, which is must be a closed loop, which is A, P, Q, B, A. A, P, Q, B, A. Closed loop. Okay. Then what shall I do? I must use Kirchhoff's second law. I must use what? Kirchhoff's second law. Okay, where Kirchhoff's second law says what? Kirchhoff's second law says total EMF is equals to sum of EMF is equals to the algebraic sum of product of current times with resistance. So it will be this, you bring to the other side, is equals to 0. Correct? Okay. So what I do now, I start with which you can start whichever point you want to start, but I choose to start with A. That's why I put A first. A, P, Q, B, A. You can also start B. B, A, P, Q, B. As long as you follow anti-clockwise. Okay? Alright, but because this book already given anti-clockwise, so you follow lah the loop. Okay? Alright, so now what we do, this is loop number 1. Okay, let's start. Okay, now we go from here. We go from here. We go from here. Okay, let me take another color pen. Okay, we go from here. Okay, when we arrive here, we notice that the loop arrow is opposite to the voltage arrow. Okay, so when loop arrow is opposite to the voltage arrow, so it will be negative voltage here, which is I1 R1. Okay, opposite, because potential positive is this side, but the loop arrow is going opposite side. So it will be minus I1 R1. We don't bother about current arrow already. Current arrow is only for the first law and also to get the voltage arrow. Now we only see loop arrow and voltage arrow only. Okay, now we go from here. We go from here. There's nothing here. Then there is nothing here. And then there is nothing here. And then when we come here, we notice that the voltage arrow and the loop arrow is opposite. That means this side is positive, but loop arrow is going this side. So we put negative I R1. Okay, because the voltage at this is I R1. Okay, and then we have a EMF there. So the loop arrow, it follows. The loop arrow what? The loop arrow follows the voltage arrow. So it becomes positive E1. Okay, then we come here, come back to point A. That's it. So therefore equals to 0. So we bring E1 to the other side. We get E1. Okay, E1 equals to this one we bring to the other side. We get E1 equals to I1 R1 plus I R1. Okay, so this one is number 2. Okay, alright, that's not enough. We have to apply another. We have to at least choose 2 loops. Okay, we already took one. Now we're going to look at number 2. Okay, alright, so I can take this whole thing or I can take this, but I'm going with the book because the book says it's taking this, so I'm going. So the book already drawn the direction of the loop, so I'm going to just follow. Okay, so it's still anti-clockwise. So what I do is I'll start from here. I can also start from here, anti-clockwise. I can also start from start from here. Okay, so I start from here. P D C Q P. Must go back to P because it's a closed loop. Okay, then I apply Kirchhoff's second law again, where total E is equals to total IR, and total E minus total IR is equals to 0. Okay, now let's do this together. I follow here, I follow here, I follow here. Okay, then what happens? The loop arrow and the voltage arrow opposite. So it will be negative E2. Okay, then I follow here. Loop arrow opposite to the voltage arrow. Opposite. Then what do? I minus the voltage here, which is I2 times with R2. Then I follow, and then I notice voltage arrow and loop arrow opposite. Okay, so I will have minus I2 R2. Okay, then I follow here. I still have to go back to P. So I go here, I notice loop arrow is same in the direction, same direction with the voltage arrow. So I put positive. Positive I1 R1 equals to 0. Okay? Alright, so what do I do now? I bring negative E2. I bring whatever positive to the other side. I2 R2 plus I2 minus I1 R1. Okay, I don't want to leave my negative there, so I times negative. So I get E2 equals to I1 R1 minus I2 R2 minus I2 R2. So I make it more, I arrange it. Okay. Okay, so I get plus, minus I2 R2 plus small R2. 1. Okay, correct? So equals to E2. This is number 3. Okay, so this is how you solve Kirchhoff's law. Okay, let's look at the book. Let's refer to the book. The book is using a very the method is very, they jump. They're actually using the same thing, but they jump the steps. Okay, so once you are very good in Kirchhoff's law, you can do the same thing. You also can jump few steps. Okay, so here they got E1 equals to I1, this one, which is this one. I'm going to focus on this E1 capital, this one, which is same. Okay, all right. Now next is they got the answer will be E2. Okay, I'm going to look at this. Yeah, E2 I1 R1 minus I2 R2 plus capital R2 plus small R2. Also they got the same. Okay, all right. So we have how many equation? We have all together 3 equation. Okay, 3 equation. The first equation is from the current law. The second equation is from the second law. The third equation is also from the second law. So we have 3 equations. We can solve simultaneously our mathematical way, and then we can find all the unknown variable. So the most important thing here is to understand current arrow, voltage arrow, loop arrow. First thing, draw current arrow. Okay, then look at the current arrow, get the voltage arrow. Okay, then after that you draw a loop arrow. From loop arrow, look at the voltage arrow and get the equation. Alright, okay, so that is all, class, for this figure. Another application of Kirchhoff's law will be for resistors in series and in parallel. Kirchhoff's law are applied in the derivation of the expression for the equivalent resistance of resistor connected in series and in parallel. So I'm going to show you an example. I'm going to draw a 3 resistor. Okay, 3 resistor which is fixed to a power supply. Okay, this is a positive, this is a negative. Okay, this resistor is R1, this is R2, this is R3, and the EMF of the cell, I'm just going to label it as V. Okay, alright, so we are going to use Kirchhoff's law for this circuit. Alright, so first thing what we are going to do is we're going to draw the direction of current. So definitely current flows in the from the positive terminal of the battery. So I'm going to call this I. I'm going to label this as I. Okay, and then after that this will be point P and this will be point Q. So what I do next is I will draw a voltage arrow. Okay, so remember this now, the 3 lesson was, first thing is to draw a current arrow. Okay, current arrow, which I have drawn already, the current arrow. Okay, current arrow, and then from the current arrow I can apply Kirchhoff's first law, where the current, I just take any junction here. So I notice the current is the same. Current in is the same as current out. So from the first law, the same current flows in all the resistor. Okay, so this one will be Kirchhoff's first law. Okay, next what I do is I draw an voltage arrow. So the voltage arrow will be the direction of positive voltage. Okay, so if it is in this direction, the current is in this direction, so the voltage arrow will, positive voltage arrow will be in the opposite direction. Same goes to here. Same goes to here. Okay, and then here for the EMF, it will be in this direction. Okay, positive, negative, it will be in this direction. Okay, so once I've already drawn the voltage arrow, I can apply Kirchhoff's second law. Okay, just to make you all know that this is actually resistor in series. Okay, after that, second law, what I can do is, I want to apply, there's only one loop, so I'm going to label this as PQ, and I'm going to label this as R, and this is S. So there's only one loop, so I'm going to take PQ R S P. Now when I do that, PQ R S P, I draw the third arrow, which will be the loop arrow. So I take P, Q, R, S, P. Okay. Okay. So from the loop arrow, I can start. So since I want to start from P, I choose to start from P. So I follow. Okay. So as I'm going here, you notice I'm going against the loop arrow is against the voltage arrow. Loop arrow is against the voltage arrow. So I will have negative I R1. Correct? The voltage here will be negative I R1. Then I go forward, and then I notice that it is the loop arrow and the voltage arrows are in positive direction. So it will be negative I R2. Okay? If it's in the same direction, if the loop arrow is the same direction as the voltage arrow, then is positive. Okay, then I flow here, I notice also they are in the opposite direction. So it will be negative IR2, it will be negative IR3. Then flow, I come here and I realize that the voltage arrow and the loop arrow are in the same direction. So I put plus V equals to 0, because once I reach P, it becomes equals to 0. So therefore, what do I get? I get V equals to I R1 plus I R2 plus I R3. So I R1 plus R2 plus R3. So V, the potential difference or the EMF of the cell, will be IR. Okay, where R is called as the effective resistance. So therefore IR is equals to I R1 plus R2 plus R3. So R is R1 plus R2 plus R3. Okay, so to find the effective resistance in a resistor itself, this will be the formula, which I know you are familiar with when you studied in your form 5. And then we know current is same from the first Kirchhoff's law. And then we also know the voltage will be from this. We can say that the voltage of the resistor V equals to V1 plus V2 plus V3. So this will be the resistor in series. Okay. Alright. Okay, that's all, class. In parallel. Okay, let's look at resistor in parallel. I'm going to draw the circuit here. I have a EMF which I'm going to label as V. Okay. Alright, so then here we have a resistor R1, okay, and then we have another resistor R2. You can draw as many as you want, but I'm just going to draw 2 to apply Kirchhoff's law in this circuit, okay. Alright, so here the current flows here. I'm going to, okay, first thing first, yeah, I'm going to draw first a current arrow. Okay, let me go step by step here. Okay, first thing, what should I do? I should draw a current arrow. Okay, so now I choose to, because this is an EMF, I choose to draw the direction of the current arrow from the positive terminal I. Okay, so here will be I1, here will be I2, then here also I2, then here is I1, and then here will be I. Okay, and I'm going to label each loop as this is A, this is B, this is C, D, E, F. Okay, so after drawing the current arrow, I apply Kirchhoff's first law. So I'm going to choose any junction that I want. Okay, so I'm going to take this particular junction here. Okay, this particular junction here. Okay, so current going in, sum of current going in I equals to sum of current coming out, which is I1 plus I2. Okay, Kirchhoff's first law. Sum of current going in is same as sum of current going out. So I get the first equation. Okay, then next what I'm going to do is I am going to draw the next arrow, which is the voltage arrow. Okay, so just a reminder, how do we draw the voltage arrow? If this is the resistor, the current is in this direction, we draw a voltage arrow for positive rise, which will be the direction opposite to the flow of current in the resistor. And then if this is the EMF, then it will be in this direction, which will be the potential rise. Okay, alright, so now we apply here. Since here the positive will be in this direction, current is flowing here, so the positive direction will be in this, okay, towards this direction, and current is flowing here, so I draw a positive in this direction. So I have to draw for all my EMF and for all my resistance. So I've already got here 3. Okay, next what do I do? The next step is to draw a loop arrow. Okay, so draw a loop arrow. I'm going to take from, I can choose whichever I want. There are 3 loops actually. A, B, C, F, A, 1, 2, A, B, D, E, A, 2, 3, F, C, D, E, F. There are 3 loops. So you need to have 2 loops. So I'm going to take the first loop, which is A, B, C, F, A. A, B, C, F, A. When you draw the loop arrow, you can draw, okay, since you can draw like this, okay, because I'm taking it in a clockwise, you can also draw anti-clockwise, or you can draw like a box, which I've drawn the other examples, like that, like that, like that, like that. Okay, so I'm going to draw also. Okay, I don't want to interfere here. Alright, so like this. Okay, A, B, C, F, A. Okay, right, so let's start from A. So A, B, I go to B. So I'm going against the voltage arrow. So what I should do is it will be negative B. Then I flow here, I flow here, I flow here. I will notice that my direction of my loop arrow and my voltage arrow is the same. So here is plus I1 R1, and then I come here, I go back to A, becomes equals to 0. Same goes to here. Why I had negative? Because the direction of the loop arrow and the direction of the voltage arrow are opposite. So I get V is equals to I1 R1. from the first loop. So it's number 2. Okay, now we can also apply the same thing for number 3. Okay, the second loop. The second loop, I'm going to take A, B, D, E, A. A, B, D, E, A. Okay, let's do this. A, B. I'm going, my loop arrow, yeah. So I'm going to draw a big loop arrow. Okay, wait, let me see. Okay, I'm going to draw the second loop with the green color. Okay, so I'm going to go like that. Actually, this is wrong. I shouldn't draw a loop arrow passing another, but I just want you to have a picture of what it is. Okay, alright. So here, A, B, I'm going here. So you realize here is opposite. So it will be negative V. Okay, picture that, yeah. Go to B, comes to D, nothing there, and then pass here. So when I pass here, my direction of my loop arrow and also the direction of my voltage arrow is in the same direction. So I plus I2 R2. Okay, and then after that I come back to A, so equals to 0. So I get V equals to I2 R2 is number 3. Okay, so in this I can see that the voltage, I'm going to draw back the circuit here. This one, V equals to I2 R2, V is equals to I1 R1, and then here is V. So I can say from this Kirchhoff's second law, potential is same in resistor in parallel. Okay, alright, and the current will be I equals to I1 plus I2, potential is same. So next what I should do is I have to find my resistance. Okay, so I take from here I equals to I1 plus I2. Okay, so what is I1? I1 from here is V over R1. Okay, what is I2? From here I2 is plus V over R2. Okay, so total current will be V equals to IR, will be I equals to V over R. Total voltage V over total resistance in the circuit, the total current. Okay, so here will be V over R. So according to Kirchhoff's second law, potential is same. So therefore, I cancel all. I get 1 over R equals to 1 over R1 plus 1 over R2. So I get the formula for the effective resistance. Okay, so that's why class, when you studied in Form 5, you studied all this important concept, but actually they are all derived from Kirchhoff's laws. Okay, so this is one of the application of Kirchhoff's law. Alright, okay, so they are applied in the derivation of the expression for the equivalent resistance of resistor connected in series and also in parallel. So this is resistor in parallel. Okay, thank you class. Example class, it's example 15.6, page 110 from the Oxford FAJAR, from the reference book. Yeah. Okay, in this circuit, it says that a circuit that consists of 5 resistor and 3 cells. So we have 5 resistor, 1, 2, 3, 4, 5, and we have 3 cells, 1, 2, 3. Okay, so in this question, they says negligible internal resistance, and they want us to find the value of the current I1, I2 and I3, and they want us to find the potential difference between A and B. So this kind of question, you see, got more than one EMF, we have to use Kirchhoff's law to solve this question. Okay, so let's look at this first. Now the first basic thing which I've already taught you all is we have to draw a current arrow. But in this question, they already given us the current arrow. Okay, I1, I2 and I3, they already given to us. So I'm going to just like flow it. Okay, I'm just going to draw for all the resistor and the cell so that we can have a better view when we apply the voltage arrow. So here will be I3, here will be I3, and here will be I1. Okay, alright, that's it. Okay, so now we already got the current arrow. We apply Kirchhoff's current law, which is the first law. So we take a junction. Okay, so I choose to take the junction here, and then when I take here, the current flowing in will be I1, current flowing in will be I3, and current flowing out will be I2. Okay, so the sum of current in I1 plus I3 equals to I2. Okay, alright, so this will be the first equation from the current first law. Okay, sorry, Kirchhoff's first law. Alright, so the next one will be is to draw a voltage arrow. Is to draw what? A voltage arrow. So just a reminder of what we know before. If the resistor is like this and the current is in this direction, then we draw the voltage arrow in the positive potential rise, where the voltage arrow will be opposite to the direction of the current arrow. Okay, and then if it's a EMF, so it will be in this direction, potential rise. So I draw for all these 5 resistor and 3 cell. So for R1 it will be in this direction. For E2, for R5, for I1, for E1, for R4, for E3, and for R3. Okay, alright, so I've already drawn for all those 5 resistor and 3 cells. Okay, next, after drawing a voltage arrow, I choose to label each point here. So since this is A, this is B, I'm going to call this C, I'm going to call this D, I'm going to call this E, and I'm going to call this 5 for each junction or point. Alright, so now I want to draw a loop arrow. Loop arrow. Okay, loop arrow. But in this question, they have already given you the loop arrow, so you no need to draw. So you follow whatever is given to you. Okay, so I'm going to take the first one. Okay, before that, the loop arrow can be in any direction. It can be clockwise, it can be anti-clockwise. Okay, if they don't give, you can choose whichever you want, but the book choose to do this in clockwise for the first loop, which is C, A, B, D, C. So I'm going to draw here C, A, B, D, C. Yeah, the book already draw, but I just want to draw a more better picture, so when I explain, you can understand what I'm trying to say here. Okay, so I start from C. I try to get the two equation for the two loops. I'm starting for the first loop, which is C, A, B, D, C. Okay, from the first one, follow. Okay, follow, and I realize that it's opposite direction, so it will be negative I1 R1. Okay, and then it comes here, CAB comes here, direction is same, so plus E2 is, I'm going to put E2 first, yeah, E2. Okay, then come here, direction is opposite to the loop arrow, so minus I2 R5. Then follow, direction of the voltage arrow is opposite to the direction of the loop arrow, so minus I1 R2. Okay, then follow direction is same. So plus with 8 equals to 0. Since it goes back to C equals to 0. So now I replace all those value. Okay, negative I1 R1 is 2 plus E2 is 4 minus I2 R5 is 4 minus I1 R2 is 2 plus with 8 equals to 0. So then I will get here negative 4I1 minus 4I2 is plus 12 equals to 0. So if I reshuffle and bring it to the other side, I will get I1 plus I2 is equals to 3. I divide also by 4. I divide by 4. So I get I1 plus I2 is equals to 3. So this is my second equation. Okay, this one is my first loop. Okay, my next loop, I'm going to follow the book also. The book choose to go it in anti-clockwise direction. So you can start whichever point you want to start, but I want to start with A. So A, as long as it's anti-clockwise, A, B, F, E, A. Okay, A, B, F, E, A. Alright, so let's start here. Okay, we come here, or before that, let me draw the anti-clockwise. Okay, come here, we follow here. So we are going in the same direction. I'm going to take a different color pen. Okay, so direction is same as the loop. So it will be positive 4. I'm going to straight substitute the value inside your class. Positive 4. And then I come and follow here. Direction. Okay, direction is what? Opposite. Okay, opposite. Direction is opposite. So minus 4I2. Okay, and then you come here, you follow here, you follow here. Direction is opposite. So you minus 3I3. Then you follow here, same. Direction is same. So plus 10. Then here direction is, sorry, not current, yeah. Direction is opposite. Not current, yeah. Direction is opposite. So minus 3I3 equals to 0. Not this current direction, yeah. Voltage arrow and loop arrow. Okay. Alright. Current direction is to get the Kirchhoff's first law. The second one is to use voltage arrow together with the loop arrow. Okay. Alright. So we get this. Then we solve this. So here will be 14 minus 4I2 minus 6I3 is equals to 0. So therefore I get 4I2 plus 6I3 is equals to 14. Okay, divided by 2. 2I2 plus 3I3 equals to 7. So this is my third equation. Okay, 1, 2, 3. Then we can solve with our maths simultaneous equation. Okay, let's see what shall we do here. I'm just going to bring the equation over here. I1 plus I2 is equals to 3 is number 2. And then I have I1 plus I3 equals to I2 is number 1. So how shall I solve this? Okay, here I think I'm going to replace I3 with, or I'm going to replace I3 here with this equation. So from number 1, I3 is equals to I2 minus I1. I'm going to substitute, this will be number 4. I'm going to take this number 4 and I'm going to substitute inside number 2. Inside number 3. I'm going to substitute inside number 3. So 2I2 plus 3 I2 minus I1 is equals to 7. So 5I2 minus 3I1 is equals to 7. So I get here number 5. Okay, and then number 2 is I1 plus I2 is equals to 3. This one is number 2. So I take number 2, I times with 3. You can do your own way, class. I'm just trying to solve this. 3I2 equals to 9. Okay, so I'm going to see this equation and this equation. Okay, so I plus negative 3I1 plus 3I1 gone, right? So 5I2 plus 3I2 is 8I2. Okay, I2 not I1, I2. So 7 plus 9 is 16. So I2 is 2 ampere. Okay, already got I2. I substitute in number 2. So I1 plus 2 is equals to 3. So I1 is equals to 1 ampere. Okay, then I take this 2. I substitute in number 1. So I get I1 1 plus I3 is equals to 2. So I3 is equals to 1 ampere. Okay, so I got all my answers. Okay, let me just I2, I1, I3. Okay, answer the question already. Okay, the next question will be, they want us to determine the potential difference between A to B. So potential difference between A to B, I'm going to answer here, yeah, is VAB. Okay, so this one is from here to here, so it's an open loop, yeah, so it's not a closed loop. If it goes back, then it's a closed loop, it's an open loop. So we start from here, we just start from this place here. Okay, we start, and then it is opposite, the direction that we follow. Okay, or maybe I will do like this. Okay, we start from here, we go here. Okay, so then you compare with the direction that you're following with the voltage arrow. So this is you are following, so direction is same, so you put plus 4, and then you come here, the direction is opposite, so you minus I2 R5, which is 4. Okay, so you substitute the value positive 4 minus I2 is 2 times 4 is 8. So plus 4 minus 8 is negative 4 volt. Okay, so VAB is negative 4 volt. Alright. Okay, so this is the potential difference between between A and B. Alright, so that's all, class. Example 15.6. Okay, thank you. Example, which is 15.3 from page 108 from your Oxford FAJAR reference book. Okay, now the question here is, they tell us that the cell of EMF 1.5 volt and 3 volts are connected in series with two resistors of resistance 2 ohm, 3 ohm as shown in the circuit diagram. Determine the potential difference between PR and QR. They want us to know the potential difference PR, and the second one, they want us to know the potential difference QR. Okay, in this circuit, we have two EMF, so definitely we have to solve Kirchhoff's law. Okay, now we have to find the current in the whole entire circuit in order to find the potential difference from this point to this point, or this point to this point. Okay, so I'm going to do what now? I'm going to draw a current arrow. First step. Okay, current arrow. So I can choose whichever I want to draw, whichever I want to follow here or follow here, I can choose. So I decided to follow from this direction, from this positive terminal. So I'm going to label this. Okay, so they are all in the same current, I. Okay, they are all I, same current, I. Okay, and then next what I'm going to do is I'm going to draw a voltage arrow. If you draw the current arrow, you can also use Kirchhoff's first law, but it's not necessary actually, because if you look at the point, the same current in, same current out. So I is equals to I, because it's only one in, one out. Okay, so now we draw a voltage arrow. Okay, so this one will be in this direction. Okay, this one will be in this direction. This one in this direction of potential rise, and the same goes to here. So for all the two cells and also for the two resistor, I've already drawn the voltage arrow. So now what I want to do is I will draw a loop arrow. So they never give, so I will just draw whichever I want and whichever point I like to start. So I choose to start from P. I want to go from P. Maybe this one I put as S, this one I put as Q. Okay, so I go P, R, Q, S, P. Okay, I'm going to go in the direction of what? P, R, Q, S, P, which is this direction. Okay, so let's start from there. As I'm going, okay, I notice that the direction of the voltage arrow is in the opposite direction of the loop arrow, so it will be negative 1.5. okay, and same goes to here. Direction is opposite, is same, direction is same, so plus with I 2. Okay, so direction is same for this one, same, so plus with 3. And then flow here, direction is also same as the loop arrow, so plus 3I equals to 0. Okay, so here I get 1.5 plus with 5I, I get 0. So I get 5I equals to negative 1.5. Okay, so my answer will be I equals to negative 0.3 ampere. Okay, when you get like this kind of negative 0.3 ampere, and then sometimes your answer is 0.3, you don't get negative, it's okay, because the direction of your current and the direction of the one that they given are opposite direction. Okay, so if that means the actual direction is in this direction, is opposite. Okay, so don't freak out if you get a negative and the other person get a positive. Okay, check out the direction of the current in the circuit. Alright, so now you get I equals to negative 0.3 ampere. So now we want to find the potential difference between P and R, which is VPR. Okay, so VPR means P to R. Okay, let's follow this one. VPR, that means from this point to this point. I'm going to follow in this direction. Okay, let's follow. I'm going to take a different color pen. Okay, I'm going to take this. Okay, so as I follow, I notice that my direction of my voltage arrow is opposite to the direction of my of the direction that I flow. So it will be negative 1.5. Okay, and then I flow, and I notice this direction follow to the direction I flow. Okay, the direction that I'm actually following here, you see I'm following the same direction, so it's plus 2 and I is negative 0.3. And I'm going and I'm following, and I notice my direction of following, which I've drawn in this pink color pen here, and the voltage arrow is the same, so I plus with 3. Okay, so VPR is so now I solve this. So what do I get? Negative 1.5 minus 0.6 plus with 3. Okay, negative 1.5 minus 0.6 plus with 3. So I get 0.9 ampere. Okay, all right. So next one they want us to find is VQR. VQR. That means from this point to this point. So I'm going to use another color pen. I don't know whether you can see that. Okay, VQR is from this. Oh, no ink. Okay, never mind, this one. This point to this point. Okay, so I'm going to follow in this direction. So then I follow now. I notice the direction that I follow is same as the direction of the voltage arrow. Then I plus with positive to negative 0.3 I, the current that flows there. Then I flow. This one is I follow the direction of the positive arrow, so I plus with 3. That's all. Okay, so negative 0.6 plus with 3, I get 2.4 ampere. So that is it. Okay, so 1 point to 1 point you don't equals to 0 because it's not a closed loop. So you just follow. As you go, you follow the voltage arrow until you reach to that particular point. Okay, so that will be example 15.3. Okay, right. Thank you, class.